Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Radiation Detectors Part 1 under the topic, under the paper Nuclear and Particle Physics. After completing this module, the students will be able to number 1 understand the basics of radiation detection. Number 2, properties of good radiation detectors. And number 3, basics of interaction of radiations with matter. Now, radiation detection basics. In this slide, basically a flow chart is shown where, and this flow chart is basically to show what happens in a typical nuclear physics experiment. Now, in this flow chart, the story begins with the source of radiation. That is, there has to be a source of radiation, and the source of radiation can either be a radioactive source or a data coming out of some experiment. So, source of radiation is there. Once the source of radiation is there, then the another component which is needed is the detection setup. Detection setup means that the objects which basically trap the radiations and basically detect them. So, that is why it is called the detection system. In the detection system, the important thing is the interaction with matter. So, when the radiations enter in the detection setup, they interact with matter. Out of that interaction, they will either produce the electron ion pairs or electron hole pairs, and if we apply a suitable voltage across the detector, we get a typical signal coming out of the detector. So, signal means a voltage pulse is basically obtained at the output of the detector. Now, to get the meaningful information from this voltage pulse, we need to basically process this pulse. Process means we need to pass this pulse into a number of electronic modules, and then this unit is called signal processing unit. So, signal has to pass through a number of electronic modules, and then we get the data, or we get the signal either in terms of some number or in terms of some spectrum. Now, looking at the spectrum or the number of counts that we have obtained, we make an analysis of the data, and then out of that analysis we interpret the data. Means we interpret various components of the nuclear experiment that happened. For reliable results, perfect understanding of every component is essential. That is, the system should be optimized. It means out of all these components which are shown in the flow chart, every component is important in itself. If we lack any of these components, or if any of these components is not perfect, we cannot get the reliable information in the experiment. Radiation detection basics. Now, in this slide, basically a block diagram is given. This block diagram, this is the block diagram of an experiment, nuclear physics experiment. Firstly, there is a source of radiation. Source of radiation can be a radioactive source or radiation coming out from some experiment. Then radiations are basically detected by some detectors placed around the setup or placed around the source. Detection of radiation is through the interaction of matter. Depending upon what kind of radiations are there, they interact with the matter of the detector and then give some meaningful signal, which can be either voltage or current. Then this signal is basically processed with the help of some electronic modules, and after the signal processing, basically we can obtain the data in terms of either the number or in terms of spectrum or in terms of any visual which we may like according to our experimental need, and then finally we need to interpret that data. For reliable results, perfect understanding of every component is essential, which means that the entire system should be optimized. We will know that what all sort of radiations we know and which can be detected by the detectors. For detection point of view, radiations can be classified as heavy charge particles. Heavy charge particle means whose mass is greater than or equal to 1 atomic mass unit, and the radiations which fall under this category are alpha particle, protons, fission fragments, etc. Then we have another category as light charge particles. Light charge particles means their mass is very small. Examples are beta particles, positrons, Auger electrons, etc. Then there are electromagnetic radiations. Electromagnetic radiations are not particles, they are basically radiations or energy. Under this category we have X-rays, gamma rays, Brahmslang radiation, etc. Then we have neutral particles. Neutral particle means like neutrons. A radiation source may emit several different kind of radiations. So it means when some nuclear activity happens, nuclear activity means either a radioactive source decays or we are doing some experiment, then the outcome of that experiment or the outcome of the decay is that several different type of radiations may be emitted. Energy spectra of particle or radiation can be discrete or continuous. So in this slide we have discussed number of radiations. These radiations either have discrete energy spectrum or continuous energy spectrum. Radiation detection basics. Now in this slide we will be discussing that what are the basic features of radiation detector. Now quantities of interest in radiation detection. Quantities of interest means when we intend to detect one radiation, what are the things that we want to know. So in this slide basically it is shown that quantities of interest in radiation detection are, sometimes we need the mass and charge of entering radiation, means we need to get the mass information and charge information of the entering radiation. It means in most of the cases these two things are needed when we want to find the energy of the particle. Second important thing of our interest is flux of entering radiation. Sometimes we want that how many radiations per second are coming in the detector. So for that purpose, position and time of entering of radiations is important. Then another important things that we want in nucleophysics experiment or when we intend to detect the radiations are the direction of entering radiation. We want to know in what direction the radiation is coming and what is happening. Also another quantity of interest is rate of entering detection. Rate of entering detection means at what rate the radiations are entering in the detector. So we have seen that for whenever we intend to detect one radiation and in the some nucleophysics experiment, then our motive or our interest can be in various things like mass and charge of entering radiation, energy of the particle, flux of entering radiation, position and time of entering, direction of entering radiation and rate of entering radiation. So all these are very useful parameters. So not all the things are needed in every experiment, but depending upon what kind of physics we are addressing and what we want to know, we can get any of these information in our experiment. Now the question arises, why so many different detectors are there? Why can't we use the same detectors for all purposes, for all in all the experiments? Why there so many different kind of detectors are available? Now we want to see that what are the factors which demand variety of detectors. The first among them is the variety of radiations. As we have seen that we have different kind of radiations, some are charged particles, some are uncharged particles, some are massive particles, some are massless particles. So, and all these, since we have different category of radiations, so these radiations interact with matter differently, so they need different kind of materials for their detection. So variety of radiations basically is the important thing which basically we need to consider, and in order to do that we have to make various kinds of detectors. Second important thing is the different quantities of interest. Different quantities of interest means, since sometimes we want to know the position information, sometimes we want to know the energy information, sometimes we want to know the charge of the incoming radiation. So at various times, depending upon our physics, basically we are interested in looking at different parameters. So since we need to know the different quantities of interest, so we need different kind of detectors. Another important thing which basically make us to choose different categories of detector is that wide range of energy radiation. Now if you talk about gamma radiations start somewhere around close to 100 keV up to several MeV, several hundred MeV. So now you can see that variety of energy are available for a given radiation, and at all energies not the same detector can be used, because depending upon the energy of the radiation, interaction pattern changes, and due to the change of interaction pattern we need to have a different kind of detector. So since the wide range of energy of radiations are available, so different level of interaction is there, and therefore we need different detectors. Radiation detection basics, challenges. In this slide, basically we are going to discuss what are the challenges when we intend to detect the radiations coming from some nuclear activity. So challenges in nuclear radiation detection. The important challenges are, first challenge is that we can't see the radiation. Since we cannot see, so it means we cannot judge it by visual. Another important complication is that we can't smell it. So radiations cannot be smelled. So it's very difficult for our senses to detect the radiation. Then we can't hear it. So if some nuclear activity is going on, we never know because no sound is produced. So we can't hear it. Also we can't feel it, and we can't taste it. So it simply means that our senses cannot detect whether some radiations have interacted with our body or not. So it's basically we can say that we cannot detect radiations by conventional means. So we need to go for some special means to detect the radiations. Good thing is that radiation produces ionized pairs to try to create an electrical signal. Now good thing about radiation is that radiation when interact with matter, they produced ion pairs like electron ion pair or electron hole pairs, and when electric field is applied, we get an equivalent electrical signal. For radiations, for different kind of radiations, ideal detector properties basically can be discussed. For example, for alpha particle, very thin or no window or ability to put source inside detector has to be there. Why this special requirement should be there for alpha particle? We will discuss it in the coming slide. For beta, the detector should have almost the same properties as for the case of alpha, but additionally can be the material of the detector can be low or high density material, or can be gas, liquid or solid medium. For gamma radiation, the detector should be of high density material, high atomic number material. So these are the properties which are required for the material of the detector if we wish to detect these radiations. For neutrons, low Z materials are preferred and most preferable materials are hydrogenous materials. Why all these requirements are there for detecting these different radiations? We will come to know in the coming slides. Radiation detection basics principles. So we continue our discussion about the radiation detection basics. Here in this slide, we are going to discuss the principle of radiation detection. Now, we know that when the radiation enters, the radiation sees the matter in terms of its constituents. That is, the entering radiation cannot differentiate between different kind of materials like whether it is gold, whether it is copper, whether it is aluminum, but all the radiations when they enter in the material, they see the matter in terms of its constituents, that is electrons and nucleus, and interact with materials by ionizing atom. This is the case for every kind of radiation which is entering in the detector. Another important thing is, while it is difficult and sometimes impossible also to directly detect radiation, it is relatively easy to detect the ionization of atoms in the detector. That is, to measure the amount of charge created in the detector, like electron ion pairs, electron hole pairs. Also, use ionization products to cause a secondary radiation. Radiation detection basics principle. Basically, we will be discussing the principle of radiation detection. Use free energized electron to produce light photons. We can measure or detect these interactions in many different ways to give variety of information. So it means when the radiation interact with matter, then some things are produced, either they are the charge particle pairs or light photons. The important parameters to detect any kind of radiations are three: stopping power, range and stopping time. These are the three important parameters which are crucial in determining or in choosing a particular material to make radiation detectors. Characteristics of an ideal radiation detector is that it should have high probability of interaction with the detector material. That is, the material of the ideal radiation detector should be such so that its probability of interaction with the incoming radiation is high. Second, large amount of charge created in interaction process. That is, when the radiation enters and interact with the material of the detector, large amount of charge should be created. The principle of radiation detection. Here in this slide, we can see one table is given. In this table, different materials are being given and the energy required to create electron ion pair in them, or electron ion pair or electron hole pair. The energy requirement to create electron hole pair or electron ion pair is given. For air, the energy required to create an electron ion pair is 34 electron volt. In silicon medium, the energy requirement is 3.6 electron volt. For germanium, it is 2.8 electron volt. In gallium arsenide, it is 4.8 electron volt, and silicon oxide, it is 17 electron volt. Now these energy requirements are a measure of how many ion pairs will be generated when the radiation interact in these different materials. It gives us an idea that if suppose 1 MeV gamma photon is hitting these materials, then we can find out how many radiations, how many ion pairs will be created, because to create one ion pair we know the value of energy required. Another important thing is that charge must be separated and collected by the electrodes. So when the radiation hits the detector material, it creates ion pairs, and ion pairs means there is a positive charge, there is a negative charge. So charge must be separated by the electrodes, and in this process, as there can be recombination, so opposite charges, since opposite charges are, recombination must be avoided. So we need to put some extra effort to make sure that the recombination of the ion pairs produced doesn't happen. Initial generated charge in detector Q is very small, example around 10 to the power minus 13 coulomb. So signal must be amplified, that is external amplification like amplifier should be connected or used, or internal amplification like multiplication of charge numbers in detectors must be done. These two methods basically maximize the signal voltage coming out of the detector system, because V is equal to Q by C. Charge Q is increased, capacitance depends upon the size of the detector, which is fixed. So if Q increases, V increases. Radiation detection types. We are going to discuss what kind of detectors are available for radiation detection. So classification as per outcome means when the radiation hits the detector, what is the result of that radiation interaction. According to this classification, the detectors are classified as gas detectors. Gas detectors means in this kind of detectors, volume of some gas, or you can say that some gas is filled between two electrodes, and when the radiation enters in that chamber containing gas, then electron ion pairs are produced. The examples of such kind of gas detectors are ionization chamber, proportionate counter, and Geiger-Müller tubes, which are commonly known as GM counters. Another category of detectors are the scintillation detectors. Interaction produces ultraviolet or visible light, which means that in scintillation detectors, when the radiation hits the material, rather than ion pair creation, the molecules of the material get excited, and then when they de-excite, they produce light. Examples of such kind of detectors are inorganic scintillator like sodium iodide, cesium iodide, and organic scintillators like plastic. We will discuss these detectors in the coming slide in bit detail. Another category of detectors are solid state detectors. These are basically made of semiconductor materials, and semiconductor crystals in the form of diode are basically used, and electron hole pairs are created. Examples of such kind of detectors are Celli detector, jelly detector, HPGE, clover, cluster detectors, or PIPS detectors. The types of detectors we have. In this slide, we are going to study what kind of detectors we have according to use. So classification according to use. In this category, we have three kinds of detectors. One are called counters. Counters count number of interactions occurring in the detectors. So they give the outcome of these kind of detectors is basically a number. They just give us number, and number corresponds to how many interactions of radiations are happening in the detector material. Another category of detectors are called spectrometers. Spectrometers yield information about energy distribution of radiation. So counters do not give us any information on the energy of the radiations, but spectrometers give specific information about what was the energy of, or what is the energy of radiation entering and interacting with the detector material. Then we have another category of detectors called dosimeters. Dosimeter yield the net amount of energy deposited in the detectors. So they give basically gives the energy deposited, amount of energy deposited in the detectors. Radiation interaction with matter. So, when the radiation comes within the detector or comes inside the detector, then first of all it has to interact with the material of the detector. So, we need to understand and we need to know what kind of interaction or radiation will have in a detector. So, knowledge of process is important from detection quality point of view. Entering radiation sees matter in terms of its constituents, electron and nucleus. It means when the radiation enters in the material, it does not see the material as if the material is gold or silver or silicon or germanium or whatever it is. It does not see like that. It sees the matter only in terms of electrons and nucleus. So, in that way, basically it interacts with either electrons or nucleus of the material medium. The basic interaction mechanism. We continue our discussion about the interaction of radiation. So, basic interaction mechanism are for charge particle. Charge particle means like for alpha particle, for protons, for fission fragments, for heavy ions. Coulombic interaction for all kind of charge radiations. So, this is the most important kind of interaction or the way of losing energy, because incoming radiation is a charged particle. Material medium has electrons as well as nucleus, both are charged. So, when the radiation enters, it interacts with the electrons of the medium and nucleus of the medium. In that way, we can say that there will be interaction between the two charged particles, and which is better called the Coulombic interaction. Due to this interaction, there is loss of energy for charged particle. Another kind of interaction within the material medium is the nuclear interaction, but this happens only for very low energy charged radiations. In the nuclear interaction, the incoming radiation, incoming charged particle interacts with the nucleus and loses its energy. Third important kind of interaction is radiation energy loss. This is relevant only for beta particles. What radiation loss? That when the electrons enter in the detector, they are accelerated, or there is a, because when the electrons enter in the detector, they see the electrons of the medium, the interaction happens. Due to the interaction, scattering of electron takes place. So, there is a continuous change of direction of electrons in the medium, because of which we can say that the electrons are always in accelerated motion in the medium, and because they are energetic, they are accelerated, so they lose energy in the form of Bremsstrahlung radiation. So, radiation energy loss is another important way of losing energy for charged particles. Then we have another category of radiations like X-rays and gamma rays. They have a completely different kind of interaction with the material of the detector. The interaction is photoelectric, Compton scattering and pair production. Then we have neutrons entering in the detector. They also have a different way of interacting with the material. Neutrons, as we know, they are the massive particles but uncharged. So, they cannot interact with the material through any electromagnetic interaction. So, neutrons interact with material medium through strong interaction, and they are detected by having reaction with the material medium and with the production of secondary radiation. Then the secondary radiation is detected. So, neutron detection in the medium is through the detection of secondary radiation. The neutrons have short range and interaction probability is very less as compared to charged particles or gamma rays. Interaction leads to complete loss of neutron and emergence of secondary radiations. Mostly the heavy charged particles like P, D, T and alpha are emitted, which are then detected by the material. So, students, Let us now summarize what we have learnt in this module. Now, we have seen that in this module, we have discussed various concepts. Now it is time for us to recap what we have learned out of that discussion. The first thing that we have learned is that detectors are important element for information about radiation. Second important thing that we have learned is that detectors detect radiation through interaction with matter. Third important thing is as radiations of different detector, as interaction of different radiations with matter is different, so variety of detectors are in use. Another important thing that we have learned is that choice of a detector primarily depends upon the type, energy and flux of the radiation to be detected. Thank you very much.